Hello everyone, welcome to our second tutorial video. So in this video we are going to discuss on an example that is plate with a hole, and that is actually a classic example for any discussion regarding the stress concentration. We in this video we will discuss on how we can actually predict the region where the concentration might be happening, and also on the ways using which we can resolve the issue of the stress concentration. So first of all, this is something that I have taken from this book, Peterson Stress Concentration Factor. So at end of the video, I will put all the links of this references that you can further read to increase the knowledge on the stress concentration part. And there are other good videos that also talks about, that is by Ansys Innovation. It comes under Ansys Innovation courses. So that talks about how we can avoid some artificially high stresses that might be caused due to some numerical issues. Similarly, there are very good blogs and videos by Tony on this stress concentration. So I will put the links in the description. So for time being, this in this example, what we are going to do is that we are going to take an example of a plate with a circular hole subjected to some uniaxial loading. And the loading is something that is going to, we are assuming, is going to be applied in seconds. So it means that we are solving some type of static analysis system. And next is that we are not going to go into some plastic region type of thing. So we are assuming the material is made up of completely made up of linear materials. Now I had already set up the model. So what I will do is that I'm not going to create any CAD geometry for this tutorial. So I had already created a plate with a whole type of thing geometry, and I'm going to demonstrate all the procedures, and we are going to discuss further on the post processing and other tips and tricks to counter this stress concentration behave means to capture this stress concentration behavior in a more accurate fashion. So first of all, like as we in the last video, as we discussed, that you can directly drag and drop any of the analysis system in the workbench project schematic, and after that you just have to define, either you can import the geometry or you can create the geometry inside the space claim itself. So let me open this window. So before going into the modeling part, so let me pull the one note. So if you are familiar with the modeling environment for the static analysis, so for all the solvers, irrespective of any of the simulation tool that you are going to use, you will see that the static system or any static problem that you plan to solve, either using Ansys, Abacus, Hypermesh, Altair, LS-DYNA. So the first assumption is that the solver on which all this algebraic equations are going to be solved is using a Newton-Raphson method. And Newton-Raphson method by default doesn't allow any rigid body motion. So if any rigid body motion occurs into your model, that solver is bound to fail. So to avoid this, like if you look at this problem statement, this is completely your force-based problem. So we are applying a force on both the sides. So as we don't know the any means, as there is no displacement constraint for this problem. So if we are trying to directly solve this problem, we are going to run into rigid body motion error. Now, to avoid this rigid body issue, what we can do is that if we look at the loading, so this full body is made up of a single homogeneous material. So if we look at the loadings are quite symmetric about your y-axis and about the x-axis. So we can use the symmetry feature that is usually available in most of the finite element method tools and simplify the problem as shown in the image B. So here you can see what we are trying to do is that we are trying to apply some type of symmetry boundary condition which will restrict the movement of both the edges in the normal direction, but it can still stretch in that corresponding direction. Like if we look at in this region, so whatever the nodes that are going to be present in this location cannot move in y direction, but those nodes can still move in the x direction. So assume this circles as a ruler. type of thing. So they can roll, but they cannot penetrate in this specific direction. Oh, let me just pull this model. So what I will do is that let me quickly go through this. So after importing the geometry, so if you go to the geometry, I had extracted a quarter of the model. So first thing is that you can assign the material properties using this assignment option. So I'm using the default structural steel. Next is that if you want to check the material properties data, you can go to this material tab and cross verify the material properties values that will be defined under the structural steel. And I am using this point because I'm going to do some type of comparison with the analytical expression. So for time being, I'm ignoring any Poisson's effect for this specific model. Now, after that, as we are only taking the quarter model, so we need to define some type of symmetry. So for adding the symmetry, you can, for a time being, because I had already defined, so the symmetry boundary condition is present here. Otherwise, you can click on the model, insert, and here you will see the symmetry option. Now, once the symmetry tab is present, if you right click, you will get different options. So each option is actually designed for modeling different type of symmetry conditions. Like if your model is cyclic symmetry, condensed cyclic symmetry, then we can use a cyclic region. Similarly, symmetry region, linear periodic, it means that if a structure is actually repeating in some specific direction, then we can use the linear periodic symmetry boundary condition. So these things maybe I will cover in upcoming one of the tutorial. But for time being, as we want to define some type of symmetry region, so you can click add this symmetry region. So once you add the symmetry region, you have to select the face. After that, you have to define the symmetry normal. So if we are going to look at this face, the normal is aligned along the x direction. So I'm using a global coordinate system, but in some cases, it might happen that your system is already in some random oriented direction and you need to restrict only the normal direction movement. So in those cases, you can create your own coordinate system and use that coordinate system to restrict the movement in that local coordinate system, X, Y, and Z axis. Similarly, you can see I had defined one extra symmetry region for this side and the third one is on this face. Now let me do one thing just for those. So suppose if I go with the default mesh setting, so this mesh looks actually a little bit coarser. After that, I'm applying a pressure. So that is pressure of 100 MPa. Now, if we are going to solve this model, we will get the stresses, like equivalent stresses like this. Now, the first thing is that if we look at this result, the first thing by looking at the result, we can say that the stress is something like the higher stress is happening in a very smaller region of this full model. So now, one thing is that whenever this type of issue happens, so one thing is that we can, instead of plotting the averaged one, because by default there is some average algorithm that will be available for all of your finite, means any of the finite element tool, it uses some type of averaging scheme to give you an averaged contour that will look a little bit smoother. So just to get a better idea and the feel how the stresses are getting developed for each element, you can use the unaveraged values. Now, once you use the unaveraged values, you will get an idea how these stresses are varying inside one element. Now here, if we look at this thing, so only at this corner node, the stresses are very high. And if I'm going to use a probe just to show, so 298 and 160. So you can see just for one element, the stresses are getting decreased from around 300 to 160. So this is a very drastic reduction in stress for any single element. Now the next thing is that suppose if we want to plot the stress along this length, so what you can do is that you can add, let me just remove this thing. Suppose I want to plot the stresses along this edge. So I can add any of the stress quantities that are present here. So for a time being, let's go with the normal stress. So what I want to do is that I want to plot the normal stress in the y direction along this edge. So under the geometry selection, you can directly select this edge, and normal stress orientation you can change as a y axis. So if I'm going to change it to y axis, I will get a stress variation along this edge. Now, the next thing is that in this case, I'm not able to see how my stresses is varying as means as a function of length along this edge. So suppose if I right click and convert to path result. So if I'm going to convert it as a path result, then if I go to the graph, I will get a better feel like how these stresses are building as a function of length along this edge. So you can see this parameter is going starting from 0 going till 50. And if we measure the length of this edge, so you can once you select this edge on the bottom, you will see this thing like edge length is 50 mm. Now if I'm going to look here, I will also see means we can also see that from starting from 0 to 50, the stresses is varying from 89 or 90 to 313 MPa. Now the next thing is that because we already figured out that there is some type of a stress concentration that is happening in the model. Uh, so what we can do is that we can now try to figure out how we can actually resolve this issue, or how we can actually how we can capture these things in a more realistic way. So for that, we can define some type of finer mesh, at least in the local vicinity of this region where your higher gradients are happening. So one or another way of figuring this out is that usually ANSYS provides an option like you can plot the error. So if you plot the error, you will get a idea that in which region the stresses errors are something that are very high compared to the other region of the other part of the model. So here we can see this is actually these are the reason in which if I'm going to refine the mesh, I might be able to capture the gradients more accurately. So because now what we can do is that there are different ways in which we can define the local controls. So one is that suppose if you are going to add the sizing, so you can locally control the sizing for this specific phase, or you can also define the edge distribution. So if you like just to showcase, so suppose if we select the edge, we can control the number of division across the edge also. So there are different ways, but the idea is going to be the same. Like we are going to put a refined mesh in the region where the gradients are high for the model. So for this case, what I'm trying to do is that I'm trying to define some sphere of influence, because when we plotted the error, we can see that this was the reason in which the error was something that was measure, uh, error was happening, and for most of the part of the model, the error was very small. Now another thing what I did, because I want to also capture how the stresses are actually building in the stress concentration region. So for that, I added one extra inflation layer just to make sure that there are going to be six around 10 layers in the thickness direction. So we can call it as a thickness direction. So now we are sure that by creating this type of mesh, that the whatever the values that we are going to get will are definitely going to capture in a in a accurate manner. Now let's solve this model. Once we solve this model, now if you look at the results, so for that, if you remember the last discussion for one element that we were doing, is that inside a single element itself, there was 50% reduction in the stresses. But now, if we look at this result, so the gradients are varying smoothly from one position to another position. And if you look 300 and 231. So previously at this location somewhere, the values were around 160. So the results are getting captured, or the gradients, mainly not results, we can say that the gradients are getting captured more accurately once we refine the mesh. So whenever we are dealing with any stress concentration type of problem, so what I will suggest few things. First is that plot the unaveraged stresses. That will give us a better picture of what is happening inside the model. Second is that if you are working with ANSYS, then plot the error. So that will give you the reasons where the refinement is something that is necessary. And after that, you can use the meshing controls. So these meshing controls will allow you to locally control or locally refine the mesh in the regions where the stress concentration will be happening. Okay. Now, another thing is that if I go back to this, because this is just to showcase, I had taken the classic example of uniaxial case of plate with a hole subjected to some type of uniaxial loading. Now, if we look at this thing, what we can see is that for this classic example, the values of the shear concentration, or mainly the whatever the stresses that we are applying here, is going to get magnified by 3 times. But if we compare this results, like normal stress that is happening here, and at top of this one, let me add this stress also, normal stress at this location. So it is somewhere near to 100. So it is getting increased by more than a factor of 3. So can you just guess what might be happening inside this model? Is it something that we are getting is result is realistic, or means we are missing something? Okay. So if we look at this analytical, whatever the expression that has been derived of means whatever for this 3 kt, that is stress concentration factor. So one assumption is that this plate that we are assuming here is something that is infinite in length. So that is one thing that is actually causing the change in the results. Because now if we look at the finite element model, it's not actually infinite. We are working with some finite domain. Now just to verify this one, let's note down this value 328. So what I'm expecting is that suppose if I'm going to increase the size of this domain, so this values, whatever the maximum value that I'm going getting here, is definitely going to reduce. So let's test it quickly. So let me open another model. So in which case, what I did is that I intentionally increased the computational domain size, even though the this whole size is fixed, but I had increased this size of the domain. Okay. So here you can see the size of the domain is very high compared to the rate. Okay. So if we are going to look at the normal stress in the x direction along this edge, we can see now we are moving closer to the analytical values that we usually get. That is kt is equal to 3. So that is we are getting near to 300 MPa along this edge. So I think if we convert it as a path, we'll get a little better clarity. So you can see at starting at 0, it's 305.04 MPa. And if you are going to further increase the computational domain, it will match more closely with uh, the analytical value that we usually get. That is stress concentration of 3 for uniaxial loading for infinite plate with a hole. Now to summarize the video, that what we discussed is that even though you are working at an assembly level, and if you see some regions where the gradients are very high compared to the other part of the model, so it's good practice, like first plot the unaveraged stress, so that will give you a better clarity on what's actually happening in that region. Now, even after plotting the unaveraged stress, if you see the gradients are simply like jumping from one element to another element, or even within one element, if there is a drastic difference in the stress values, then you can use the meshing control feature to refine the mesh in the local vicinity where the gradients are happening. Now, one thing to highlight here is that wherever your gradients are high, so usually if we look at the reason, mainly the reason that might get affected. So if we compare it with a plate with a hole example, we can see that even though it's starting from 3 uh, times of the stress value, but just after one diameter away, it reduces back to your the same stress value. So usually it is something that you can look at the Sant-Vinant principle. So yeah, that will help you uh, to actually decide. Like usually, you can start with a very smaller reason. Like if you have some fillet, so what you can do is that you can take for 3 times the fillet radius or something like that, or for 3 to 5 times of the fillet radius, and see that how the gradients are getting captured if you refine the mesh at least in that specific region. Like here, as in this image, as you demonstrated, like what I did is that I added one inflation layer. So because this was a very simple example, so it was easy to add the inflation layer, but that not be a case for your actual industrial applications. So for those cases, you might need to use other refinement practices. But there are many features inside the Ansys Mechanical uh, meshing capabilities that will help you to refine the mesh locally. Only thing is that keep in mind that idea is to capture the gradients means in a correct fashion. So the next thing is that is I'm also sharing some of the references. Like if you are interested in working with different type of notch or fillet type of applications, groups, holes, keyways, threads, and so on. So you can refer this Peterson. This is a very good book on the stress concentration, and it is well appreciated in an industry. Next is that I'm sharing another link, stress singularity, stress concentration. That is another topic that we will discuss in some coming videos. But you can go through this article. So this is a very good article on stress singularity, stress concentration, and the mesh convergence study. So mesh convergence study, even though I have not touched, but you can just whatever we are discussing is that to capture the gradients, we need to refine the mesh. So the same thing is the mesh convergence study. We keep on refining the mesh unless and until we get a good trend or the flattening of the stress versus refinement in mesh. So you will get an idea after going through this article. Again, you can go through this video. This is a very good video available on Ansys Innovation under Ansys Innovation courses. Now, I will also put the link of that videos by Tony, so you can go through this video. This is a 1 hour lecture series, so but it is quite informative. So that's all for this video. Uh, See you in the next tutorial. Thanks.